Okay, so today we're looking at a scatter plot, and we've got our line going through it, and you can see that it's going in an upward direction. Points are pretty close, and what we have over here is the equation for this line. Okay, so um, what do you notice and what do you wonder? This is just kind of your observations on this. We notice that the points are pretty close to the line. The line is going probably about through the center of where those points would be, and this is called a line of best fit. Okay, now you can use this line to estimate different things about this problem. Since it's the number of people and the maximum noise level, I'm not exactly sure what this is talking about, but maybe it's talking about concerts or maybe just a crowded area of people talking. So, but obviously these data points have something to do with numbers and decibel levels. Okay, so we're going to look at the lines of best fit and the different parts of it, the slope, the y-intercept, and correlation coefficient. Okay, so an acoustician, I'm not sure how to say that, someone who studies the science of sound, created a scatter plot to measure the loudest measured noise compared to the amount of fans in the arena over the course of a few months. Okay, so the number of people would be the fans in the arena, and this is the number of decibels that their noise is. Okay, so the more fans, the more noise. Predict the maximum noise level when 75,000 fans are present in the area. So now what we're going to do here is we're going to use our equation to predict the, the level. Okay. Okay. So what we're going to do is it's 75,000. Now it says the number of people in thousands. So we're just going to put in 75 into the X. Now we could go up here and there might be a point. But what we're looking at is we're trying to find the actual value that's on the line to predict what it's going to be. So this point about right here, it looks like, might be where that 75 is. And when you plug this in, 1.5 times 75 plus 22.7, you end up with 135.2, which is about where that point is going to be, 135.2 decibels. Okay, using the model, predict the number of people present if the maximum noise level is 120 decibels. Okay, so again, decibels would be on our Y value, so we're going to put the Y value here, 120. Okay, we're going to subtract the 22.7, and that gives us 97.3. We're going to divide that by 1.5, and that tells us that 64.9 thousand people there. So that's 64,900 people. Okay, now it says, what is the slope of the line of best fit? So it's 1.5 is the slope, and that means for every 1,500 people, the decibel goes up one, or the volume goes up 1 decibel, okay, because it's 1.5 over 1. Okay, well, actually, that would be the other way around. For every 1,000 people, the decimal level, decibel, not good at saying that one, decibel level increases by 1.5. Okay, now what is the y-intercept of the line of best fit? So the y-intercept, remember, is when x is 0. So that would basically take away this value, and your b in the equation is the y-intercept. So we have y equals 22.7 decibels when x equals 0. Now, what does this mean in the context of the scenario? With no people present, decibels are at 22.7. Okay, so either this is random noise in the arena, or this is, since it's just a prediction, may not even make sense. Okay, yeah. Okay, it says estimate the correlation coefficient for this data and justify your thinking. Now, we don't have the actual numbers here for these points, so we can't use Desmos like we did the other day to create the R value, but we can estimate this. We know it's going to be positive because the slope is positive, and these are really close, so I'm going to say probably a 0.9 or maybe even a 0.95, okay, somewhere between those two because they're real close together. Okay, so our next one is a food markup. I'm going to slide this up a little bit to see more of the question. Okay, so the sale price of several food items, Y, that's how much they're selling the food for. The cost of the ingredients used to produce those items is the X value, as well as a line that models the data. The line is represented by that equation. So it's saying here that as the cost of the dollar, as the ingredient costs go up, the cost of the food goes up. Okay, the food you're selling. Okay, so what is the predicted sale price of an item that has ingredients that cost $1.50? Okay, so if you look here, $1.50, you have a point here, but it's not on the line. So we can look and we can see it's around $6. So let's put that in. $1.50 is the X value. So we're going to put in, I hate it when that happens, 3.48 times 1.5 plus 0.76. So that's what we want to type in to our calculator. Okay, so that would be, oh, be careful where you put your decimals, decibels, decimals. Yeah, golly, I'm not talking well tonight. Um, make sure you put it in the right place. Okay, so this is $5.98. Like I said, it was close to, it looked like it would be close to 6 at the 1.5 line. Okay, um, so the next one says, what is the slope of the linear model and what does it mean? Well, the slope is $3.348, so that means for every $1 in ingredient cost, the sale cost or the sale price increases by $3.48. Okay, what is the y-intercept of the linear model? Well, that would be 76 cents. So it says, what does this mean in this situation? So that means that if the ingredients cost nothing, no cost for ingredients, the sale cost is 76 cents. Okay, and that it's asked, does this make sense? Well, no, it doesn't make sense because you have no ingredients, so you have nothing to make, therefore you can't charge anything for nothing. So this does not make sense. Okay, now that's going to happen sometimes on these lines of best fit, mainly because they are lines of best fit. They're estimates. They're not exact values in our situation. Okay, it says the scatter clock compares points per game to free throw attempts per game. So we have the number of points a player makes in basketball and the number of free throw attempts per game. It's represented by this equation. And the X is the free throws, and the Y represents the points per game. Based on the model, how many points per game would you expect a player who attempts 4.5 free throws per game to have? Okay, so here is where we're looking at. So we're looking somewhere between 15 and 22.5. So we're going to put 4.5 in for X. So we're looking at approximately 20.2 points per game. Okay, and that would make sense. We're below the 22.5, but we're above the 15, and it's closer to the 22 than it is the 15. So 20 sounds good. Sounds like a good estimate. Okay, so you just plug in the values and you use your equation to estimate. It says, what is the slope of this model's prediction line? Well, the slope is 4.4 approximately. So for every one free throw, you can expect to have 4.4 points per game for every one free throw attempt. Okay, again, what does the slope mean in the context? Well, we just talked about that. It means that for every one free throw that you go up about 4.4 points. Okay, what would be a good estimate of the correlation coefficient for this line of best fit? Well, they're clustered down here, but then out here they get a little spread apart. I would say this is probably going to be closer to maybe a 5 or a 6, maybe a 0.55. How about that? We'll say approximately a 0.55. It's not real clustered, but it's not a too terribly weak value because it's got some really close. Most of those are really close to the line. So, I mean, you can't really go wrong on this unless you just go completely 1 or 0 here, or if you go into the negatives, because it is going up, so it needs to be positive. But somewhere in the middle, I would say, because it's not a great fit, not a great association, but it's not too terribly scattered. Okay, so our last one here, it says a researcher creates a scatter plot that displays the relationship between the number of years in business and the percentage of the company's business that is fair trade. And it gives the definition of fair trade here, helping developing companies promoting sustainability. So we get this line of best fit, and when the business owner wants to know a prediction of what percentage of the company should be fair trade after being in business for 20 years. So remember, X is the years in business. So that means we're going to plug in 20 here into the equation. Okay, so if I typed this in right, what percentage of the company's business is fair trade? They should expect 1.88% fair trade. That's not a whole lot. Okay, so the showing your work part would be the 0.091 times 20 plus 0.060, and then you'll just plug that in to get your 1.88%. Now, obviously, this is in percent form because if we put it out of that, that would be 188%, which wouldn't make sense because that would mean over more than their business is worth in fair trade. Okay, so this would be the prediction that he would give for the businessman. Okay, so let's look at the next one. The correlation coefficient is 0.75. What does this tell you about the relationship between the number of years a company is in business and the percentage of the company's business that is in fair trade? So it has a strong positive well, we'll say a fairly strong positive linear association. Okay, so as the business grows, for every year the business is in business, they increase by 9% each year. Okay, 0.09% each year. So that would be our correlation coefficient for this data. Now, you have a agree-disagree statement here. We'll go to it. Oh, there it is. Okay, so using this scatter plot with this equation, they want you to go through and find, okay, it's not doing. Let's see. Okay, it's not letting me roll. Okay, so they're going to ask you to agree or disagree with some statements about this model. So again, we're using the equation, so make sure that you use the equation, plug it in, either solve for the y if you're given the ingredient cost, solve for the x if you're given the sales price, but find your values using your equation and explain what you have. Okay.